What if the universe isn't just vast, but filled with secrets so profound they could rewrite everything we think we know? From invisible forces shaping galaxies to mysterious signals from the great unknown, the cosmos is a puzzle humanity has barely begun to solve. Today, we dive into 25 of the most confounding mysteries that continue to baffle astronomers and scientists alike. Could there really be an unseen force pulling entire galaxies toward it? Or is there a chance ancient radio signals from deep space are messages from intelligent life? These questions are only the beginning. Each mystery brings us one step closer to understanding the enigma of existence itself. So, are you ready to explore the unknown and uncover the mind-bending secrets of the cosmos? Let's begin. Now turning to the first mystery on our cosmic journey, we encounter the Great Attractor. This enigmatic force is a gravitational anomaly so powerful that it's pulling entire galaxy clusters, including our own Milky Way, toward it at staggering speeds. But what exactly is the Great Attractor, and why is it so difficult to unravel its secrets? Part of the challenge lies in its location. It sits behind what astronomers call the zone of avoidance, a region of the sky heavily obscured by the dense dust and gas in the plane of our galaxy. This makes it nearly impossible to observe directly with conventional telescopes. Despite these obstacles, scientists have managed to study its effects through the motion of galaxies in its vicinity, noticing how its immense gravitational pull influences the cosmic dance of celestial bodies. Some theories suggest it could be a massive conglomeration of dark matter and galaxy clusters, while others propose it might point to an even larger structure in the universe known as the Laniakea supercluster, of which our galaxy is just a small part. Whatever the true nature of the Great Attractor, it challenges our understanding of the universe's large-scale structure and reminds us how much more there is to discover. With the next phase of the journey in sight, let's explore another elusive force shaping the cosmos. With the next phase of the journey in sight, we delve into the perplexing enigma of dark energy. Imagine a force so mysterious and all-encompassing that it accounts for nearly 70% of the entire universe. Dark energy is the term we use to describe this invisible phenomenon that is not only present everywhere but is also driving the universe to expand at an ever-accelerating pace. This discovery, made in the late 1990s through observations of distant exploding stars known as supernova, shattered our understanding of cosmic dynamics. Before this, scientists believed the universe's expansion, which began with the Big Bang, would eventually slow down under the pull of gravity. Yet, dark energy defies this expectation, working against gravity to push galaxies farther and farther apart. The questions surrounding dark energy are as vast as the cosmos itself. What is its true nature? Could it be a new kind of energy field filling space, often referred to as the cosmological constant? Or could it signify that our understanding of gravity, based on the theories of Albert Einstein, needs to be fundamentally revised? Some researchers even speculate that dark energy might hint at dimensions beyond those we can perceive, or that it could be linked to the quantum properties of empty space. Despite years of investigation, dark energy remains one of the most significant unsolved mysteries in astrophysics. It challenges our grasp of the forces ruling the cosmos and leaves us questioning the ultimate fate of the universe. Will the universe expand forever, dispersing galaxies into a cold, dark void? Or does dark energy hold secrets we have yet to even imagine? As we ponder these cosmic riddles, let us move forward and uncover another invisible architect of the universe. Now turning to another profound cosmic enigma, we arrive at the mystery of dark matter. If dark energy is the force propelling the universe to expand, dark matter is its silent counterpart, binding the cosmos together. Unlike the matter we are familiar with, which makes up stars, planets, and even ourselves, dark matter is completely invisible. It neither emits nor reflects light, making it impossible to observe directly. Yet its existence is undeniable, as its gravitational pull influences the motion of stars and galaxies. Scientists first suspected dark matter's presence in the early 20th century, when astronomers noticed that galaxies were rotating at speeds that could not be explained by the visible matter they contained. Simply put, there was not enough observable mass to account for the gravitational forces holding these galaxies together. Something unseen had to be at work. Today, dark matter is estimated to make up about 27% of the universe, a staggering figure considering that ordinary matter accounts for just 5%. So, what could dark matter be? One leading theory suggests it might be composed of weakly interacting massive particles, or WIMP, hypothetical particles that interact through gravity but barely with anything else. Other possibilities include actions, extraordinarily light particles that could behave differently from anything we have ever encountered. Some researchers even speculate that dark matter could consist of primordial black holes formed in the early universe, or entirely new forms of matter that defy our current understanding of particle physics. Despite decades of research, no direct evidence of dark matter particles has been found. Experiments deep underground or in space designed to detect these elusive components continue to yield intriguing but inconclusive results. This leaves us with compelling questions. Is dark matter a particle, a wave, or something beyond our imagination? Could its mystery hold the key to unlocking a deeper understanding of the universe's structure and origins? As we marvel at this hidden framework of the cosmos, let us step further into another profound mystery tethered to the skies above. As the next challenge unfolds, we find ourselves exploring the perplexing phenomenon of fast radio bursts, or as they are commonly called, fast radio pulses. These are incredibly brief yet immensely powerful bursts of radio waves originating from the depths of space. Lasting just a fraction of a second, they pack more energy than what our sun emits in an entire day. The mystery, however, lies in their origin. Despite being discovered in the early 21st century, we still do not know what produces them. Pinpointing their exact source has proven to be a daunting task. The sheer speed of these bursts makes them incredibly elusive, and their detection often depends on being in the right place at the right time. Imagine trying to find the source of a single, unpredictable flash of light in a vast, ever-changing sky. This challenge has been likened to searching for a needle in an astronomical haystack. Over the years, however, advancements in radio telescope technology have allowed scientists to make some headway. A handful of fast radio bursts have now been traced back to specific locations, such as distant galaxies, giving us clues about their possible origins. Proposed explanations range from neutron stars with extreme magnetic fields, known as magnetars, to the merging of compact objects like black holes or neutron stars. And then, of course, there is the more speculative idea that these signals might even be created by advanced alien civilizations. While the latter theory captures the imagination, there is no concrete evidence to support it. Yet the thrill of unearthing these cosmic mysteries keeps researchers worldwide glued to their instruments, driven by the hope of catching the next burst and perhaps one day decoding its secrets. Could fast radio bursts be the first whispers of events or phenomena we have never encountered before? As we ponder this, let us move forward to yet another enigma written into the fabric of the cosmos. Now turning to the next profound mystery, we delve into the enigmatic inconsistencies in the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This faint, almost uniform glow of microwave radiation permeates the universe, serving as a snapshot of its infancy, mere moments after its birth. However, even in this seemingly smooth and consistent canvas, scientists have discovered peculiar anomalies that defy easy explanation. One such anomaly is the cold spot, a region unusually cooler than its surroundings. What could cause such an irregularity in a phenomenon so fundamental to the universe's early history? Some suggest that it might be a mere statistical fluke or the result of a vast supervoid, an immense region of space with fewer galaxies than expected. Others entertain more exotic possibilities, such as it being evidence of interactions with other universes, lending weight to the ever-intriguing multiverse hypothesis. Still, there are those who wonder if this anomaly hints at unknown physics or processes that our current understanding simply cannot yet grasp. The cold spot is not the only intrigue, as smaller, less pronounced variations across the cosmic microwave background continue to pique curiosity and fuel debate. These subtle deviations challenge our models of cosmic inflation, the rapid expansion of the universe in its earliest moments, and compel scientists to question whether we fully understand the universe's origins. Each new observation pushes us closer to untangling this cosmic puzzle, but also reminds us of how much we still do not know. Could these anomalies be messages encoded within the universe itself, urging us to probe deeper and question more? With this question lingering, let us proceed further into the vast mysteries that await us. Moving forward, we encounter another profound enigma in the realm of space exploration, the Pioneer Anomaly. This puzzling phenomenon revolves around the unexpected deviations observed in the trajectories of the Pioneer 10 and Pioneer 11 spacecraft. Launched in the early 1970s, these robotic pioneers were humanity's first messengers to venture into the vast unknown of interstellar space, carrying with them golden plaques that encapsulate the story of life on Earth. As they journeyed beyond the far reaches of our solar system, scientists noticed a subtle but persistent slowing effect on their motion, an unexplained deviation from the paths predicted by established physics. What could be causing this mysterious force acting upon these spacecraft? One proposed explanation suggests that thermal emissions, essentially heat radiating unevenly from the spacecraft, might generate a minute thrust sufficient to alter their trajectories. This idea, while plausible, has sparked debates due to the need for precise modeling and extensive data analysis. Another, more daring hypothesis points to the possibility of modified gravity, which would imply that our understanding of the fundamental laws governing the universe is incomplete. This scenario raises profound questions about whether the force of gravity itself behaves differently over vast distances. Despite years of investigations and countless simulations, no definitive answer has yet emerged, leaving the Pioneer Anomaly as an open question in the annals of cosmic exploration. Could this subtle nudge in the spacecraft's path offer us a clue to the deeper workings of the universe, or is it simply a reminder of the limits of our observational precision? As we ponder these possibilities, the mystery of the Pioneer 10 and 11 continues to inspire and challenge scientists, standing as a testament to the complexities of navigating and understanding the cosmos. As the next challenge unfolds, we arrive at one of the most thought-provoking questions in the cosmos, the Fermi paradox. It is a paradox that challenges our very perspective on the universe and our place within it. On one hand, the sheer size and age of the cosmos, coupled with the countless stars and planets it contains, strongly suggest that life should exist elsewhere. On the other hand, we have yet to find any definitive evidence that extraterrestrial civilizations exist. This puzzling contradiction, first posed by physicist Enrico Fermi, raises a simple yet profound question: where is everyone? To explore this enigma, scientists have proposed a variety of intriguing explanations. One possibility is the rare Earth hypothesis, which theorizes that the conditions necessary for life are so precisely tuned that Earth may indeed be an exceptional case, a rare oasis in an otherwise barren universe. Another explanation focuses on a concept known as the Great Filter. This idea suggests that somewhere along the path from simple organisms to advanced civilizations, there is an obstacle so difficult to overcome that very few or perhaps no civilizations have managed to progress beyond it. Could this filter lie in the emergence of intelligent life, or is it ahead of us, a challenge humanity has yet to face? Alternatively, some have speculated that advanced extraterrestrial civilizations may intentionally avoid contact with us. Whether they perceive humanity as too primitive, too unpredictable, or simply insignificant, the idea that we are being deliberately ignored opens up profound possibilities about the nature of intelligent life. Despite the lack of evidence, the Fermi paradox continues to ignite discussions and fuel our search for the unknown. As we gaze into the depths of space, the silence surrounding us is both humbling and tantalizing. Could it be that the next signal, the next discovery, or the next breakthrough will finally provide an answer to this cosmic riddle? Or will the silence endure, inviting us to probe even deeper into the mysteries of the universe? Now turning to one of the most fascinating moments in the search for extraterrestrial intelligence, we arrive at the WOW signal. In August of 1977, astronomer Jerry Amon, while volunteering at Ohio State University's Big Ear radio telescope, stumbled upon something extraordinary. A powerful, narrowband radio signal from the constellation Sagittarius was detected, lasting 72 seconds before disappearing entirely. It was so striking that Amon circled it on the printed data with a red pen and wrote the word "Wow" in the margin, giving the signal its famous name. What made it so special? For one, the signal matched what scientists thought an intelligent, extraterrestrial broadcast might look like: highly focused and not easily linked to any known natural source. Yet, despite countless efforts to locate it again, the signal has never been detected since. This singular event has sparked decades of speculation. Some believe that the WOW signal could have been a message from an advanced alien civilization, perhaps a fleeting attempt at communication or a random snippet of interstellar activity. Others propose more mundane explanations, such as interference from Earth-based sources or even a previously undetected cosmic phenomenon. However, none of these theories have been definitively proven. In recent years, researchers have tried to retrace every detail of the event, exploring whether factors like a passing comet or a rare astronomical alignment could explain it. Despite these efforts, the exact origin of the WOW signal remains an enigma, a tantalizing clue that deepens our curiosity about what or who might be out there. Could it have been a cosmic accident, or was it the closest we've ever come to hearing from another intelligent species? As we continue to scan the skies, the hope of solving this mystery keeps our imaginations alive and our ears tuned to the whispers of the universe. Moving forward, we encounter the enigmatic phenomenon of rogue planets, worlds that wander the cosmos untethered to any star. Unlike planets in our solar system that orbit the Sun, these drifters roam freely through interstellar space. But how do we even detect something so elusive? Rogue planets are often spotted indirectly using gravitational microlensing, a technique that observes how their gravity temporarily bends and amplifies the light of a distant star as they pass in front of it. Despite these clever methods, their sheer darkness and isolation make them incredibly hard to study. What makes these planets so fascinating is the mystery surrounding their origins. Were they once part of a planetary system, violently ejected by gravitational interactions, or did they form in isolation, perhaps in regions of space dense with cosmic gas and dust? Either scenario challenges our current understanding of how planets come into existence. Yet, there's an even more intriguing question: could rogue planets harbor life? It might seem unlikely at first, given their lack of a nearby star to provide heat and light. However, some scientists speculate that internal heat generated by radioactive decay or tidal forces could create subsurface oceans beneath thick layers of ice, potentially providing the right conditions for life to emerge. This idea sparks exciting possibilities. Entire ecosystems could exist on these wandering worlds, hidden away from the light of any star. If confirmed, such discoveries would force us to rethink not only where life can thrive, but also how common habitable environments may be in the universe. Rogue planets remain an unsolved puzzle, drifting silently through the vastness of space, reminding us that the cosmos is filled with secrets yet to be uncovered. As we refine our detection techniques and expand our search, who knows what mysteries these wayward worlds might reveal? With the next phase of the journey in sight, we arrive at the perplexing enigma of Tabby's star, a celestial object that has baffled astronomers with its unusual dimming patterns. Officially named KIC 8462852, this star, about 1,400 light-years away in the constellation Cygnus, exhibits fluctuations in brightness that defy conventional explanation. Unlike regular stars whose light dimming might hint at an orbiting planet, the dips in Tabby's star's luminosity are irregular and dramatic, dropping by as much as 22% at unpredictable intervals. Such extreme dimming is far too substantial to be caused by a planet passing in front of the star. So, what could be causing this phenomenon? One leading hypothesis suggests that a swarm of cometary fragments or planetary debris may be periodically blocking the star's light. However, no direct evidence of this has been observed, leaving the idea largely speculative. Another theory involves massive clouds of interstellar dust, but the patterns of dimming appear inconsistent with this explanation as well. Then there is the most captivating speculation of all, the possibility of an alien megastructure, such as a Dyson sphere, a hypothetical construct designed to harvest energy from a star. While incredibly intriguing, this idea remains purely in the realm of conjecture due to the lack of any supporting evidence. More recent studies have proposed that intrinsic stellar processes, like unusual star spots or changes within the star itself, might be at play, though these too fail to fully account for the star's bizarre behavior. Tabby's star is a reminder of how much we still have to learn about the cosmos. Every new insight into its peculiar dimming patterns seems to raise more questions than answers, keeping this stellar mystery alive. As scientists continue to monitor its erratic light, one can only wonder if the key to its secrets lies in an entirely new realm of astrophysics, or perhaps somewhere even more extraordinary. Where science grapples with uncertainty, the allure of discovery only grows stronger. With the next phase of the journey in sight, we delve into the fascinating and mind-bending concept of the multiverse, an idea that challenges everything we think we know about reality. At its core, the multiverse hypothesis suggests that our universe might not be the only one. Instead, it could be just one among an infinite number of parallel universes, each with its own unique properties, physical laws, and perhaps even versions of ourselves. This concept emerges as a theoretical solution to some of the biggest mysteries in cosmology, such as why certain fundamental constants in our universe seem so perfectly tuned to allow life to exist. If countless universes exist, it could mean that we simply live in one of the rare ones where the conditions happen to be just right. However, the multiverse remains an unproven and highly controversial idea. Critics argue that it ventures beyond the realm of science because, by definition, these other universes would be impossible to observe or measure directly. Without empirical evidence, some researchers question whether the multiverse is even a valid scientific theory or simply speculative philosophy. Yet, the notion of a multiverse is not without merit. It finds support in certain interpretations of quantum mechanics, which suggest that every possible outcome of a quantum event could lead to the creation of a new universe. Additionally, theories like cosmic inflation propose that, in the earliest moments of existence, rapid expansion could have given rise to an infinite array of bubble universes, each separated by vast distances we could never traverse. The idea of infinite parallel universes is as thrilling as it is bewildering. It raises profound questions about the nature of reality, our place within it, and whether we will ever have the tools to prove or disprove such an extraordinary hypothesis. Could the multiverse be the ultimate answer to why the cosmos exists as it does, or is it simply a reflection of the limits of our imagination? As we ponder these possibilities, the multiverse continues to spark curiosity, debate, and endless wonder, setting the stage for the next chapter in our exploration of this cosmic enigma. With the next phase of the journey in sight, we dive deeper into the implications of the multiverse, exploring what it could mean for our reality and existence. If the multiverse is real, it would fundamentally reshape our understanding of everything. Imagine a reality where every decision you've ever made, every fork in the road, has led to a different version of you in another universe. Somewhere out there might be a world where dinosaurs never went extinct, or one where physics operates on principles entirely alien to us. The implications extend far beyond fascinating what-if scenarios. The multiverse hypothesis challenges the very concept of uniqueness and singularity, raising profound questions about identity, free will, and the nature of existence itself. Scientifically, testing the multiverse is a daunting task, but not entirely outside the realm of possibility. Some researchers suggest that physical traces of other universes might exist within our own, perhaps as anomalies in the cosmic microwave background radiation or unexplained gravitational effects. Others propose that advances in quantum mechanics and particle physics could someday provide indirect evidence of parallel realities. More speculative ideas include the potential for universal collisions, as theorized by some models of cosmic inflation. Such collisions, if they ever occurred, might leave detectable imprints in the structure of spacetime. While these ideas remain in their infancy, they represent the first steps toward grappling with questions that could redefine cosmology. If proven, the multiverse would expand our understanding of the cosmos, revealing it to be far larger and more complex than we ever imagined. But even if we never find definitive proof, the theory continues to push the boundaries of human thought, encouraging us to question, explore, and reach for the unknown. Moving forward, we encounter yet another enigma that defies explanation as we turn our attention to the abrupt drop-off in the number of objects in the Kuiper belt, a phenomenon scientists call the Kuiper cliff. Now turning to the Kuiper cliff, we explore one of the most perplexing features of our solar system. The Kuiper belt, a vast region beyond Neptune, is home to countless icy bodies and dwarf planets. However, something curious happens as we observe its outer edges. At a certain distance, the number of objects in the Kuiper belt drops off dramatically, almost as if the solar system abruptly ends. Scientists refer to this sudden reduction in the density of objects as the Kuiper cliff, and its existence raises intriguing questions about the formation and evolution of our solar system. What could cause such an abrupt boundary? One theory suggests that the Kuiper cliff may have been sculpted by a massive, unseen celestial body lurking in the distant reaches of our solar system. Some have even proposed that this mysterious object could be the elusive planet 9, or perhaps an entirely different type of planetary remnant. Others speculate that the abrupt cutoff may result from gravitational forces exerted by nearby stars during the early days of the solar system, effectively disrupting the distribution of material beyond a certain range. Alternatively, the Kuiper cliff might hold a clue to the solar system's infancy. It could represent a primordial boundary where the sun's early disk of gas and dust thinned out, leaving behind insufficient material to form more objects. Such an explanation would make the Kuiper cliff a relic from the very birth of our cosmic neighborhood, a frozen snapshot of processes that shaped not only the Kuiper belt but the solar system as a whole. Regardless of its origin, the Kuiper cliff remains an enduring enigma, offering a tantalizing glimpse into forces that operated billions of years ago at the farthest edges of our system. As we ponder this cosmic boundary, we find ourselves drawn deeper into the mysteries of the solar system's outskirts, turning next to the search for evidence of a possible planet 9, a hypothetical giant world that may yet rewrite what we know about our celestial backyard. Now turning to the search for Planet 9, we explore one of the most intriguing possibilities in modern astronomy. Planet 9, a hypothetical giant world lurking in the far reaches of the outer solar system, has been proposed to explain strange gravitational effects observed in the Kuiper belt. Scientists have noticed that certain distant objects in the Kuiper belt follow peculiar, clustered orbits that cannot be easily explained by the known planets alone. These anomalies suggest the presence of a massive, unseen planet exerting its gravitational influence from afar. But what do we know about this enigmatic world? Theoretical models indicate that Planet 9 could be up to 10 times the mass of Earth, orbiting the Sun at an incredible distance, hundreds of times farther than Earth's orbit. Such an extreme location would make this planet incredibly faint and challenging to detect, even with our most advanced telescopes. Adding to the mystery is the sheer size of the region to search. The outer solar system is vast, and pinpointing the exact location of this theoretical planet is akin to finding a needle in a cosmic haystack. Some scientists have even speculated that Planet 9 might have been a rogue planet, a world that formed elsewhere and was captured by our Sun's gravity billions of years ago. Others suggest that it could be a remnant of our solar system's chaotic early days, a giant planet expelled to its distant orbit by gravitational interactions with its siblings. Yet, despite years of dedicated searches, no direct evidence of Planet 9 has been found. Its existence remains hypothetical, fueling debates and inspiring further investigations. Could there be an even stranger explanation for the gravitational oddities observed in the Kuiper belt, such as an entire population of smaller, unseen objects working together? Or might Planet 9 be out there, waiting to be discovered, its presence set to transform our understanding of the solar system? As scientists continue the hunt, Planet 9 remains a tantalizing mystery, a reminder of how much we still have to uncover about our own cosmic neighborhood. Moving forward, we turn our attention to another enigmatic feature of the universe, the origin of supermassive black holes, a puzzle that challenges our understanding of how the cosmos evolved. Now turning to the origin of supermassive black holes, we delve into one of the most profound mysteries of the cosmos. These colossal objects, weighing millions to billions of times more than our Sun, are often found at the centers of galaxies, including our own Milky Way. What puzzles scientists is how these supermassive black holes could have formed so early in the universe's history, mere hundreds of millions of years after the Big Bang. The timeline seems impossibly short for such massive entities to grow. One leading theory suggests they could have formed through the direct collapse of massive gas clouds. Under the right conditions, a gargantuan cloud of gas might bypass the usual star formation process, collapsing directly into a black hole, skipping intermediate stages. This scenario could explain their rapid emergence, but it requires very specific conditions that some researchers believe were rare in the early universe. Another hypothesis proposes a more gradual growth process. In this view, smaller black holes, the remnants of the first stars, could have merged repeatedly and accreted surrounding material over time, eventually reaching supermassive proportions. However, this mechanism seems to conflict with the short time available for such growth after the origin of the universe. Adding to the enigma, recent observations have uncovered supermassive black holes that appear to reside in dwarf galaxies, defying expectations and raising more questions about how they came to exist in such environments. Some scientists even speculate that exotic phenomena, like the existence of primordial black holes formed in the intense conditions of the Big Bang itself, could play a role in explaining the early presence of these cosmic giants. Yet, no single explanation fully accounts for their rapid formation and extraordinary size. The origin of supermassive black holes remains a compelling mystery, challenging our understanding of cosmic evolution and the forces shaping galaxies. As we continue to observe and question, their story reminds us of how much remains to be unveiled about the universe's earliest days. Moving forward, we journey into another cosmic puzzle, the mystery of the missing baryons, ordinary matter that seems to be hidden in the vast expanse of the cosmos. As the next challenge unfolds, we confront the perplexing case of the missing baryons, often referred to as the missing matter of the universe. Baryons are a type of ordinary matter, the kind that makes up everything we see and interact with on a daily basis, from stars and planets to people and even your morning cup of coffee. According to theoretical models, baryons should account for about 5% of the universe's total composition. This may sound small, but it represents nearly all the visible matter in the cosmos. However, when scientists attempt to locate this predicted amount of baryons, an unsettling discrepancy arises. Observations of galaxies, stars, and intergalactic gas account for only about half of the expected total, leaving the other half mysteriously unaccounted for. This baffling absence has sent scientists on a cosmic scavenger hunt, using the most advanced tools and techniques in modern astronomy to find the missing baryons. One promising method involves observing the intergalactic medium, the vast expanse of gas that lies between galaxies. Researchers hypothesize that much of the missing matter could exist in diffuse clouds of hot, ionized gas scattered across these regions. Detecting this faint material is no easy task, as it neither emits nor absorbs light in ways that are easily observed. To tackle this challenge, astronomers employ highly sensitive instruments such as X-ray and ultraviolet telescopes, capable of picking up the faintest signals from distant regions of space. These observations have already led to some breakthroughs. For example, scientists have identified what are known as galactic filaments, massive strands of gas connecting clusters of galaxies. These filaments may house a significant portion of the missing baryons, hiding in plain sight within the cosmic web that underpins the structure of the universe. Computer simulations of the universe's evolution suggest this gas should indeed be present, but direct confirmation remains elusive. Another potential hiding place for the missing baryons lies closer to home, within the halos of hot gas that envelop galaxies, including our own Milky Way. Some studies suggest these galactic halos could house the missing matter, but quantifying their contents has proven exceedingly difficult. As technology advances, new methods and observations continue to bring us closer to solving this mystery. Locating the missing baryons is about more than just completing the cosmic inventory. It has profound implications for our understanding of how galaxies form, evolve, and interact with their surroundings. Yet, despite recent progress, the search is far from over. The mystery of the missing baryons drives home how much of the universe remains unexplored, defying our expectations and fueling our curiosity. With this enigma in mind, we now shift our gaze to another fundamental question about the universe itself, the debate surrounding its shape and what it might reveal about the cosmos's ultimate destiny. Now turning to the next profound enigma, we delve into the debate over the actual geometric shape of the universe, a question that lies at the very heart of cosmology. Imagine trying to determine whether the universe is flat like a sheet of paper, open like a saddle, or closed like the surface of a sphere. These three shapes represent the fundamental possibilities for the geometry of our cosmos, and each one carries profound implications for its ultimate fate. If the universe is flat, it would mean that parallel lines remain parallel forever, and the cosmos could expand indefinitely but at a steadily decreasing rate. An open universe, on the other hand, suggests a more dramatic expansion, one that accelerates endlessly, leaving galaxies isolated in the vast emptiness of space. In contrast, a closed universe would have a curved geometry like the surface of a sphere, implying that the cosmos might eventually stop expanding and begin to contract, leading to a possible collapse known as the Big Crunch. The perplexing part, current observations have yet to provide a definitive answer. Scientists have attempted to measure the universe's curvature by analyzing the patterns of cosmic microwave background radiation, the faint afterglow of the Big Bang. These patterns act as a cosmic fingerprint, offering clues about the geometry of the universe. So far, the data suggests that the universe is astonishingly close to flat, but this conclusion comes with its own set of uncertainties. Minute errors in measurement and the influence of dark energy complicate the picture, making it difficult to rule out the other possibilities entirely. Adding to the challenge is the sheer scale of the universe itself. The portion of the cosmos we can observe is minuscule compared to its potential entirety, meaning the overall shape could differ dramatically beyond the limits of our observations. Researchers also employ large-scale surveys of galaxies to understand how matter is distributed across space, as this distribution could hint at the universe's true shape. These surveys have provided remarkable insights, but they too leave gaps in our understanding. The shape of the universe is more than just a theoretical puzzle. It underpins critical questions about the universe's origins, its ultimate fate, and even the fundamental laws of physics that govern all existence. The answer could redefine how we see ourselves within the cosmic tapestry, reminding us once again of the vast unknowns that surround us. With this unresolved mystery in mind, we journey next into the perplexing realm of black holes, where information itself seems to defy explanation. Now turning to the enigmatic world of black holes, we encounter one of the most mind-bending puzzles in modern physics, the black hole information paradox. At its core, this paradox challenges the very foundations of how we understand the universe. Imagine a black hole, a region of space so dense that not even light can escape its grasp. When matter or energy falls into a black hole, it carries with it an inherent property known as information. In physics, information refers to the unique details about the state of particles, what they are, where they are, and how they interact. The paradox arises because black holes seem to defy the fundamental principle in quantum mechanics that information can never be destroyed. Instead, anything that crosses the event horizon, the boundary of the black hole, appears to vanish without a trace, leaving behind only the black hole's mass, spin, and charge. This idea is deeply unsettling because it contradicts the laws of quantum physics, which state that information must always be preserved, no matter the process. The black hole information paradox pits two pillars of modern science against each other: quantum mechanics and Einstein's theory of general relativity. While general relativity provides a breathtaking explanation of how black holes form and behave, it offers no solution for what happens to the information swallowed by these cosmic giants. On the other hand, quantum mechanics insists that information cannot simply disappear, leading to a direct conflict between these two frameworks. This clash has sparked decades of debate and countless theories. Some suggest that information might escape through a process called Hawking radiation, a theoretical mechanism where black holes slowly evaporate over immense periods of time. However, this explanation remains controversial and incomplete, as it raises new questions about how information could be encoded within this radiation. Others propose that the information is not lost but instead stored on the event horizon itself, creating a holographic imprint akin to a cosmic ledger. Yet, even this idea faces significant challenges, as it requires a radical rethinking of space, time, and the nature of reality. The implications of resolving this paradox are profound. It could transform our understanding of the universe, bridging the gap between general relativity and quantum mechanics, and potentially leading to a unified theory of everything. For now, the black hole information paradox stands as a monumental mystery, daring scientists to uncover its secrets. With this conundrum in mind, we take the next step into exploring possible solutions, as theories and ideas clash in the quest to decode the universe's most perplexing enigma. With the next phase of the journey in sight, let us delve deeper into the proposed resolutions for the black hole information paradox, where groundbreaking ideas attempt to reconcile this cosmic conflict. One of the most prominent theories comes from the work of physicist Stephen Hawking. Known as Hawking radiation, this concept suggests that black holes are not entirely black but emit tiny amounts of radiation due to quantum effects near the event horizon. Over unimaginable spans of time, this radiation could cause a black hole to lose mass and eventually evaporate. The intriguing possibility here is that as the black hole diminishes, the information it consumed might somehow be encoded within the Hawking radiation and released back into the universe. While this theory offers a tantalizing hint of a solution, it remains incomplete. Scientists continue to grapple with how the information could be preserved and whether the radiation truly carries it in a decipherable form. Another captivating idea is the holographic principle, which proposes that all the information entering a black hole is not destroyed but instead stored as a two-dimensional imprint on its event horizon. Imagine the event horizon as an enormous cosmic ledger, meticulously recording every detail of the matter and energy it engulfs. This theory suggests that our three-dimensional reality could be a projection of this two-dimensional information, similar to a hologram. If true, this would revolutionize our understanding of the fabric of space and time. Yet, even the holographic principle is fraught with challenges, as it requires a paradigm shift in how we perceive the universe itself. Beyond these ideas, some researchers have ventured into even more uncharted territory, proposing that black holes may act as gateways to parallel universes, where information might escape into alternate dimensions beyond our comprehension. Solving this paradox does not merely resolve a single puzzle, but could lead to a profound unification of physics, bridging the gap between the quantum world of the very small and the relativistic universe of the very large. It is a quest that calls for bold theories, innovative experiments, and perhaps a level of creativity yet to be imagined. The black hole information paradox, far from being a dead end, acts as a beacon for scientific discovery, challenging humanity to rethink the limits of knowledge and the nature of reality itself. As we move forward, the enigma of black holes continues to unfold, offering clues that may one day unlock the fundamental secrets of the cosmos. Now turning to the mystery of Oumuamua, let us explore the first known interstellar object to pass through our solar system, a discovery that left scientists both thrilled and perplexed. Detected in October 2017, Oumuamua captured attention with its highly unusual characteristics. Unlike any comet or asteroid observed before, this object exhibited a strange, elongated shape resembling a giant cosmic cigar. Its dimensions were strikingly peculiar, estimated to be 10 times longer than it was wide, but perhaps even more baffling was its behavior. Oumuamua experienced an unexpected acceleration as it moved away from the Sun, a phenomenon not entirely accounted for by gravitational forces alone. This deviation from its predicted path sparked a whirlwind of theories about its origin and nature. One possibility is that Oumuamua is a fragment of a larger celestial body, perhaps ejected from its home system after a cataclysmic event. Another theory suggests it could be a hydrogen iceberg, a chunk of frozen molecular hydrogen, sublimating as it approached the Sun. This would explain its acceleration without the presence of a visible gas or dust tail, typically seen in comets. Yet, the most controversial idea posits that Oumuamua might be an artificial object, possibly a probe sent by an advanced extraterrestrial civilization. Advocates of this theory point to its unusual shape and motion as evidence of intelligent design, sparking debates that extend far beyond scientific circles. While the true nature of Oumuamua remains unknown, its journey has reminded us of the vastness of the cosmos and the potential for extraordinary discoveries beyond our imagination. As scientists continue to analyze data and develop new observational techniques, the story of Oumuamua stands as a testament to how much we still have to learn about the universe and what might be out there waiting to be found. Moving forward, we arrive at the fascinating enigma of Saturn's hexagon, a geometric wonder swirling at the planet's north pole. Unlike any other atmospheric phenomenon observed in our solar system, this hexagonal storm spans an astonishing 20,000 miles across, large enough to fit nearly 2 Earths side by side. Its sharply defined six-sided structure, first captured by the Voyager spacecraft in the early 1980s and later observed in greater detail by the Cassini mission, remains one of the most puzzling features of the gas giant. The hexagon rotates in sync with Saturn's interior, completing a full rotation about every 10 hours, yet its exact origin and stability have left scientists searching for answers. One leading theory suggests that the hexagon is a result of fluid dynamics, specifically standing wave patterns created by the complex interplay of atmospheric currents at different latitudes. Laboratory experiments on Earth have demonstrated how rotating fluids can naturally form geometric shapes under precisely controlled conditions, hinting that similar mechanisms might be at work on Saturn. However, this does not fully explain how the structure has persisted for decades, nor its remarkable symmetry. Another intriguing idea considers the role of deeper atmospheric phenomena, such as waves generated by Saturn's internal heat or magnetic field. Some even speculate that unknown forces or processes unique to the gas giant may be contributing to the hexagon's formation and longevity. Adding to the mystery, the hexagon is accompanied by a central cyclone at its core and exhibits a spectrum of changing colors from striking hues of blue to golden tones depending on the seasons. This color variation might be linked to chemical changes in the atmosphere influenced by sunlight, offering yet another layer of intrigue. Despite years of study and countless observations, Saturn's hexagon continues to baffle researchers, serving as a vivid reminder of the universe's capacity to surprise and captivate. As our exploration advances, uncovering the secrets of this celestial geometric marvel might not only reveal more about Saturn, but also deepen our understanding of planetary atmospheres across the cosmos. As the next challenge unfolds, we delve into the perplexing cosmic lithium problem, a subtle yet profound discrepancy that has confounded scientists for decades. Lithium, one of the three lightest elements formed in the minutes following the Big Bang, holds a unique place in the narrative of cosmic evolution. Theoretical models of Big Bang nucleosynthesis predict specific amounts of lithium that should exist in the universe today. However, when astronomers measure lithium levels in the atmospheres of ancient stars and across cosmic structures, they consistently find far less lithium than these models anticipate. This puzzling mismatch, often referred to as the lithium problem, raises fundamental questions about the accuracy of our understanding of the earliest moments of the universe. Some researchers propose that certain exotic processes in the primordial universe, such as the decay or annihilation of unstable particles, might have altered lithium production, reducing its abundance. Others suggest that the observed deficiency could arise from mechanisms within stars themselves, where lithium might be destroyed or depleted due to intense nuclear reactions in their cores. This would mean the original lithium is still consistent with predictions but has since been hidden from view. Another intriguing theory points to the possibility that early cosmic environments may have produced variable amounts of lithium depending on unique local conditions, offering a more nuanced explanation for the inconsistency. Despite these compelling ideas, no single solution has been universally accepted, leaving the lithium problem as an open question in astrophysics. Resolving this enigma could provide critical insights into the physics of the Big Bang, the behavior of stars, and the formation of elements, weaving yet another thread through the intricate tapestry of our cosmic understanding. With each observation and experiment, scientists inch closer to uncovering this element's elusive story, driven by a shared commitment to untangling the mysteries of the universe. As the journey continues, this unresolved riddle serves as a reminder of the profound gaps in what we know and the boundless potential of what we might yet discover. With the next phase of the journey in sight, we venture deep into the heart of our galaxy, the Milky Way, to uncover a particularly enigmatic phenomenon, the galactic center radio transients. These mysterious signals, first discovered in the early 2000s, have left scientists baffled due to their unpredictable and sporadic nature. Unlike typical radio bursts or steady emissions from known celestial objects, these transients appear suddenly, emit an intense blast of radio waves, and then vanish, sometimes reappearing weeks, months, or even years later without warning. Their intermittent behavior challenges astronomers' ability to pinpoint their exact source or understand their underlying mechanics. One popular hypothesis suggests that these transients might be linked to magnetars, a type of neutron star with an extraordinarily powerful magnetic field. Magnetars are known to produce bursts of energy that could theoretically explain these radio signals, but the observed characteristics of the transients do not fully align with what we know about magnetar activity. Another possibility is that they are associated with other exotic objects, such as rapidly spinning neutron stars or white dwarfs undergoing unusual processes. However, some researchers believe these signals could represent a completely new class of astrophysical phenomena, perhaps tied to processes we have yet to discover or comprehend. Adding to the intrigue, the galactic center itself is a uniquely challenging environment to study, as it is densely packed with stars, dust, and gas, all of which complicate efforts to isolate and analyze these signals. Advanced instruments like radio telescopes and improvements in signal processing have provided glimpses into these mysterious bursts, but their origins remain elusive. Could the transients be a clue to something profoundly new in our understanding of stellar or galactic behavior, or perhaps even an indirect sign of something more alien in nature? For now, these fleeting signals serve as a tantalizing hint of the secrets still locked away in the chaotic and energetic core of our galaxy. As scientists continue their meticulous search for answers, each new detection brings us one step closer to unraveling this cosmic puzzle, inspiring both awe and curiosity about the unknown forces shaping our universe. Now turning to one of the most staggering voids in the cosmos, we encounter the Boötes void, a region so vast and empty that it defies ordinary comprehension. Spanning an estimated 330 million light-years in diameter, this immense expanse contains far fewer galaxies than one might expect for a space of its size. To put this in perspective, a typical region of comparable dimensions would be expected to host thousands of galaxies. Instead, the Boötes void contains only a few dozen, making it one of the most striking examples of cosmic emptiness ever observed. This profound lack of matter has puzzled scientists since its discovery in the late 20th century. One prevailing theory suggests that the Boötes void may have formed due to the merging of smaller voids over time, leading to the creation of a larger, unified region of emptiness. This process, which aligns with the idea of cosmic evolution, hints at how the large-scale structure of the universe might have developed. Yet even this explanation fails to fully account for its extraordinary size and sparseness. Intriguingly, the Boötes void challenges our understanding of how matter is distributed across the cosmos. It raises fundamental questions about whether the universe is more unevenly structured than previously thought. Some researchers speculate that such voids might hold clues to the mysterious nature of dark energy, the force driving the accelerated expansion of the universe. Others ponder whether the Boötes void could be the result of processes we have yet to discover, leaving room for exciting possibilities. As we peer into this vast emptiness with ever-advancing technology, the Boötes void continues to spark both fascination and speculation. What secrets could such an immense, seemingly barren region hold, and what might it reveal about the forces shaping our universe on the largest scales? For now, the Boötes void remains a silent enigma, a cosmic whisper of the profound mysteries that lie hidden in the depths of space. Moving forward, we arrive at a puzzling and contentious mystery in modern cosmology known as the Hubble tension. This enigma revolves around the rate at which our universe is expanding, a value referred to as the Hubble constant. The mystery lies in the fact that different methods of measuring this expansion have yielded conflicting results. When scientists observed the early universe using data from the cosmic microwave background radiation, they calculate one specific value for the Hubble constant. However, measurements taken in the local universe, such as those involving nearby galaxies or supernova, produce a noticeably higher value. This discrepancy is not a minor one. The two results differ significantly enough that it cannot simply be attributed to measurement errors. Instead, it suggests that there might be something fundamental about our understanding of the universe that is incomplete or incorrect. Could new physics be at play, or is it possible that our current models of the universe need to be rethought? Some researchers speculate that additional components of the cosmos, such as unknown particles or forces, might account for these diverging measurements. Others have proposed that subtle variations in the way time and space behave could be influencing the results. No consensus has been reached, and this debate continues to challenge some of the brightest minds in the field. At its heart, the Hubble tension question is about more than just the speed of cosmic expansion. It strikes at the core of how we understand the entire history and future of the universe. Resolving this tension could lead to groundbreaking discoveries about the nature of dark energy, the early conditions of the universe, or even entirely new aspects of physics that we have yet to uncover. As scientists refine their tools and explore new methods to tackle this perplexing problem, the Hubble tension serves as both a challenge and an opportunity. It reminds us that even the most established concepts in science are not beyond scrutiny, and that the path to understanding the universe remains as mysterious as it is exciting. With the next phase of the journey in sight, we take a step back to grasp the bigger picture of these cosmic enigmas. Each mystery we have explored, from the Great Attractor to the Hubble tension, acts as a piece of an intricate puzzle that maps out the universe's grand design. These puzzles are more than isolated curiosities. They are windows into the fundamental laws of nature, the origins of existence, and the forces that will shape the cosmos for eternity. Together, they remind us of how much we have yet to learn and how far humanity has come in its quest for knowledge. The importance of continued exploration cannot be overstated. Each breakthrough in unraveling these mysteries brings us closer to answering the age-old questions of why are we here and what is our place in the universe. It is through this relentless pursuit of understanding that our perspective broadens, revealing not only the vast complexities of the cosmos but also our profound connection to it. The significance of scientific curiosity lies in its ability to challenge assumptions, inspire innovation, and unite us in the shared wonder of discovery. Every unanswered question fuels the drive for deeper inquiry, pushing the boundaries of what we thought was possible. The cosmos is a testament to the infinite potential of exploration, urging us to keep looking, keep questioning, and keep dreaming. In this vast arena of unknowns, the mysteries left unsolved are as valuable as the ones we resolve, for they guide us toward new possibilities and expand the horizons of human knowledge. As the next challenge unfolds, let us embrace the mysteries of the cosmos not as barriers to knowledge but as beacons guiding humanity's endless quest for understanding. These enigmas, no matter how perplexing, serve as reminders of our innate curiosity and drive to explore. It is through such mysteries that we uncover our potential, pushing the boundaries of science, technology, and imagination. Each unanswered question is not a limitation but an invitation, a call to dig deeper, to question more, and to discover what lies beyond the horizon. The mysteries of the cosmos captivate us not only because they are vast and awe-inspiring, but because they reflect our enduring desire to seek meaning in the unknown. They compel us to work together as communities and as a species in pursuit of answers that can unite rather than divide. They challenge our perspectives, proving time and again that even as we solve one puzzle, countless others are waiting to be explored. This pursuit of knowledge is not just about the answers we find, it is also about the journey itself. It strengthens our resilience, fuels our imagination, and reaffirms that, even in the face of the cosmos' immense scale, the human spirit remains undaunted. Each mystery is a testament to our shared belief that understanding the universe is intertwined with understanding ourselves. So let us continue to wonder, question, and dream, for every step we take into the unknown brings us closer to unveiling the profound truths hidden in the stars. As we conclude this incredible journey through 25 unsolved mysteries in the cosmos, one thing becomes clear: the universe is as wondrous as it is enigmatic. From the elusive dark matter and the perplexing Fermi paradox to the haunting echoes of the wow signal and the vast emptiness of the Boötes void, each mystery invites us to gaze deeper into the night sky with awe and curiosity. These enigmas are not just puzzles to solve but stories waiting to be told, each one sparking questions that remind us of the boundless frontiers that lie beyond. They are a testament to humanity's unrelenting spirit of exploration, a spirit that drives us to seek answers to the greatest questions of existence. Which of these mysteries fascinated you the most? Share your thoughts in the comments below. We would love to know what captures your imagination. And if your passion for the cosmos burns as brightly as ours, be sure to subscribe to our channel, like this video, and hit the notification bell so you never miss another adventure into the unknown. Until next time, keep looking up, for the universe is calling. Will we ever answer?